In this lecture, we will discuss about the estimation of the mean and the confidence intervals. When we talk about the estimation of the mean, then we basically mean the estimation of the population mean, because it is obvious that we are estimating the population parameters using the sample statistics. So let's take a simple example to understand this idea. We have discussed this example previously before in central limit theorem, and I just take advantage that since it is a simple one, so we can understand the idea over here quite easily. Now the thing is that suppose we had a population comprising of the values 1, 2, 3, 4, 5, 6, and let's say that we take samples of size 2 from this population. So in total we have got 36 samples. All the possible samples of size 2 are 36 over here, with the characteristics that the order matters in these samples and the repetitions are also allowed. So these are the samples that we have got. Not the problem is now we are estimating the mean, the population mean, and we don't know it. That's why we are estimating. So let's say that suppose randomly, let's take it in this way, that we can have any of these samples as our experimental data, and using that sample we would be estimating the population mean. Previously we have seen this thing, that the z-scores and the t-scores are used to determine the z and t values corresponding to the sample mean, and they are used in their particular situations. Like z-scores are used when the sample size is greater than 30 and the population standard deviation is known to us, and t-scores are used when the sample size is basically either less than 30 or the population standard deviation is not known to us. So using any of these z and t, we can find an equation or model or derive an equation, a simple equation, a statistical equation, which can be used to estimate the value of population mean. So by little rearrangement of the mathematical terms, we can see that, like for example, for z-scores, the corresponding mu can be written as x power plus minus g sigma p upon the root n, where sigma p is the population standard deviation supposedly. And using the t-scores with a little rearrangement, we can show this thing that the population mean is x bar plus minus ts upon root n, where x bar is the sample mean in both the equations and capital N is the sample size in both the equations. Now we can see that correct estimation very much depends upon the values of z and t that are taken in these equations, right? And if you can recall the z and t tables, then they correspond to the particular probabilities. So estimation very much depends upon the probabilities that we are taking. So let's take this an example, that suppose I have randomly, I have a sample with me from this population, and the mean of the sample that I have got is 1.5. Now I need to estimate the population mean parameter or population mean statistic using this sample mean, which is 1.5 available to me. Earlier we also know this thing that the sigma p upon root n, or the population standard deviation divided by the sample size square root, is 1.208. We are taking a situation that in which the population standard deviation is known to us. If there is any problem in understanding that how we reach to this value, so you can refer to the lectures of the CLT, or I have shown little calculation over here as well. So this was the population. The population mean was 3.5, and the population variance is 2.92, and the population standard deviation is 1.708. So we have these results so that when we do this estimation, we can verify, we can see that whether our estimation is correct or it is incorrect. But practically we do not have these things quite easily available. So that's why we do the estimations. So by plugging in the values of x bar and uh, the standard deviation of the sampling distribution of the mean, or SEM, which is 1.208, we get an equation which is something like this. Now over here I'm teaching you this, I'm letting you know or making you understand this estimation procedure using the z values. How we do it with the t values, we'll do it later. So when we plug in the values, the only thing remaining to know is the z, that what should be the z value. Now the answer to this question, that what should be the z value, depends that to what extent of the area we are taking, that this within this area the population mean exists. Now, this is a very important concept to understand, because suppose I say that this is my normal distribution, okay, and by my experimental procedures, I know this thing, that the mean which I'm trying to estimate, the population mean which I'm trying to estimate, I'm confident about it 99%. Yeah, or I'm confident about it 95%, or I'm confident about it 90%, or I'm confident about it 68%. What does this all means? Firstly, we should note this thing, that in order to obtain the z value, we need to have the area or the probability of the normal distribution, or vice versa. That is, in order to obtain the area or the probability, we should have the z values. So one of them should be known to us in order to get the other value. Over here in this equation for the estimation, which I'm highlighting so that we can focus over here, the only thing that is unknown to us is the z value. Okay. Now let's say by my experimental procedures, I am only 68% confident that the mean that I'm estimating is x is this value, or I'm only 68% confident that the mean lies in this area of the normal distribution, then definitely I would have the corresponding z value for it. But suppose that I am 90% confident that the mean lies in the 90% area of the normal distribution that I have, then this would give me the corresponding z value for it. If I am 95% confident that the mean lies within this area, then this would give me the corresponding z value for it. So what do we actually mean by it? Please note this thing, that the only thing that we are available with is the x bar, or the sample mean. If I say that the population mean is around 90% area of the sample mean value, right? Then that corresponding z value would be used over here. If I say that the population mean is around 99.7% area around the x bar taking as the central value, then this would give me the population mean value. Okay, so the more confidence we have, the more confident we are, the more the area would be surrounded by the, or would be surrounded around the sample mean. The less confident we would be, the lesser the area would be surrounded around the sample mean value. Okay, please note the way this equation has been written. We are actually adding or subtracting something around the sample bar, sorry, around the sample mean, which is the x bar value. So we are assuming this thing, that whatever sample mean we have got, right, this is going to be the estimate of the population mean, and the more the area will be covered around this x bar, the better will be the estimation of the population mean. Because we know this thing, the higher the value of z is, the more the area of the normal distribution is covered, and the lesser the value of z is, the lesser would be the area of the normal distribution covered. So if higher value is obtained of the normal distribution, in terms of the area, then it means the probability would be reaching to 100% value. And if lower value of area is obtained corresponding to lower values of z, then the probability would be reducing towards 0% value. So try to understand the idea what I'm trying to convey to you. The more the confident we are that this sample mean represents the population mean, or it will give me an interval in which the population mean would be present, then definitely higher this area should be. And the less the confident I would be that the area or the interval obtained by the sample mean I have got, the lesser would be the z value, or the lesser would be the area correspondingly. So let's see what do I mean with some mathematical calculations. Suppose I say that my confidence level is just 68%. I'm only 68% confident that the sample mean represents the population mean. Then this means that the z value would correspond to 68% probability. And using this empirical rule or the basic rules of the normal distribution, as you can see from the graph here as well, that by 68% approximately, we mean that we are having a plus minus 1 sigma interval, or the z value corresponds to plus minus 1. So this means that I would be substituting 1 in the z against the z value in this equation, and after doing some calculations we see that mu, which is the population mean, comes out to be 1.5 minus 1.208 to 1.5 plus 1.208. That means the interval of the population mean is between 0.292 or 2.708. Or what do we mean by this? Can be quoted in this way as well, that the population mean is present in between 0.292 to 2.708 at 68% confidence interval. This 68% confidence interval estimate is also understood in this way, that if 100 samples were taken, then out of those 100 samples, 68 would give me a population mean in the interval from 0.292 to 2.708. Now this is our estimate of the population mean. If we don't know the population mean, then this estimate is interpreted that population mean can be found in between these two values, 0.292 and 2.708, at 68% confidence interval, right? This is what we mean. But since we know that our population mean is 3.5, therefore this means that this interval estimate, although calculated correctly, but this interval estimate is not a good estimate. It actually does not contain our population mean. So what can we do? I need to change my confidence interval. I need to have a higher confidence. I need to have a higher reliability upon my calculations or upon my experiment that yes, my sample mean does represent the population mean. And this means that I need to change my z value to some higher value. Let's say that I change it to 95% confidence level, then this means that the corresponding z values would be plus minus 1.96. As we know that the z of 95% area corresponds to plus minus 1.96. And when you substitute this 1.96 and minus 1.96 into this equation, we get an interval of mu with a lower limit of minus 0.86768 and an upper limit of 3.86768, all which can be put in this way, that the mu interval or the population mean estimate interval is from minus 0.86768 to 3.86768, which basically means that the population mean lies anywhere between these two values. And since we know that the population mean value is 3.5, so definitely this also means that our estimate is much better as compared to the previous one, because this interval does contain the population mean. So by 95% confidence interval, we mean this thing that if 100 samples were taken, then out of those 100 samples, 95 of them would give me a, a mean value which lies in this interval from minus 0.86768 to 3.86768, right? And this would be the estimate of the population mean, right? Do we understand this thing now? This is a very important concept of confidence intervals in the statistical inference, and we need to understand this thing. So higher the z value, higher would be our area covered by the normal distribution. And remember that higher the area covered by the normal distribution, the more it is towards 100% value, the more certainty it brings to our calculations. Practically, this means this thing that in order to obtain more certainty, more surety about our results, we would be needing to basically improve our experimental methods, our quality methods, so that we can be more confident that yes, what we are getting is giving us the proper real answer, is giving us the proper estimate of the unknown parameter. So that's how we basically do this estimation of the population mean, and this example exemplifies it with a very simple way that how this estimate could be done. So the more the confidence interval percentage we have, the more will be the area covered, and hence the more will be the probability of estimating the population mean, or the better would be the probability. Percentage value of confidence interval, for example, 95% also tells us that out of 100 samples, 95 will have a mean in the obtained range. So this was about the population mean estimation, and this is again one other application of the central limit theorem, that it is used to estimate about the population means or other unknown parameters of the population, right? So thank you very much for this lecture. If you have any confusions, any queries, so you can either write it in the comments or contact me.